this one we used to prove equilibrium equation of 3D differential element by taking 3D stress components. Here we will see how to solve those equations. Like 2D element, we used to solve three-dimensional elements also. Same stresses will be acts, but thing is that in case of 2D elements, we used to take only thickness is unity. But in case of 3D elements, we also consider element thickness in z direction also. The stresses are acting in three directions we used to take in this particular topic. Okay, this one is a 3D stress component. This element has been chosen from one continuous body or one continuum. Okay, a solid body which is having bigger size. From that bigger size of the body, we have chosen a small element, a cubical element for that one. If you take any Rubik's cube, any one part of the small element of the Rubik's cube will be look like this. Okay, if you apply force over that particular Rubik's cube, the forces will be acts over that particular Rubik's cube will be indicated by like this. If you take, suppose if you assume as Rubik's cube, a continuum will be nothing but like Rubik's cube, then a small element if you choose from that one, the four stresses acting over that particular element, small element from that particular cube will be indicated like this. If you arrange that one into the coordinate system, in Cartesian coordinate system, you can see three components. X direction component is there, Y direction component is there, and Z direction component is there. Three coordinate systems we used to have like this. Okay, and every direction, if you take any element, that element is having the thickness. You can see here dx is the thickness in x direction, dy is the thickness in y direction, and dz in this one, dz is not zero in this equation, but in this case you can see the dz. Okay, depth of this element is dz. You can take as thickness of this element. Dz is nothing but, if you see here, this is the dz of the element. Okay, and these all coordinates are indicated with different stress components. If you see this diagram, at coordinate which is near to the x-axis, parallel to the x-axis, you can see stress sigma x is generated in this direction, sigma x. We used to indicate like this, but this will be indicated over the surface of the body. But here normally I am indicating with coordinate only. Sigma x, sigma y, and sigma z. Three stress components, principal stress components will be there. These three are acting over the, if you see sigma x here, this top face is carrying sigma x stress. Sigma x stress is acting over this particular body. Okay, and similarly that due to that force in the direction of y, shear stress will be acts, in the direction of z, shear stress will be acts. Okay, due to the same force, because of applying the external forces and body forces, shear stress is also generated in the body. Okay, this is sigma x direction. In negative sigma x direction, if you see back side of this face, this is the front side of the face, and similarly in the back side of this face, you can get negative direction, negative sigma x plus sigma x value. Negative stresses will be indicated in the negative x-axis direction. Okay. Similarly here we can see the sigma y will be acts on this plane. Okay, sigma y will be acts on this plane, and this plane also tau xy, tau yz, and similarly three components of sigma y also act here. Okay, and similarly here bottom also acts with three forces, three other extra forces. Okay, these three forces, x direction forces we used to indicate with positive direction we used to indicate with plus symbol, negative directions we used to indicate with the negative symbol, minus symbol. Okay, those are the sign conventions we used to use, and this is the stress which is taken from the continuum. Okay, continuum is nothing but a continuous body. To solve this equation, 3D stress components are differential. To solve the differential equations, we used to consider three force equilibrium equations and three moment equilibrium equations. Okay, if you consider these 6 equilibrium equations in Cartesian coordinate, we can solve the this shear stress component, and also we can solve for normal stress component. by using these 6 equilibrium equations. If you see here different type of forces are acting. Wait a second, Amma. Here we can see force components. We don't have any stress components here. Okay, stress doesn't have any components. Stresses will have the directions, and forces we can resolve into the components here. If you see here, force we can't take stresses directly. We can't solve the stress equations directly. We can solve those by taking as force components. Okay, by taking the surface area, we used to arrange in the equilibrium equation. If you see this diagram, this element, okay, this element is having 3 directions, x, y, and z, and every direction we can see the stress components. Okay, this if you see force at this particular element will be indicated by the sigma x normal stress which is acting on this particular plane. Okay, near to the 0 0 0 coordinate starting with 0 comma 0, or if you take here on the x and y coordinate, x and z coordinate. If you take x and z coordinate, this one is the x and z coordinate. On this coordinate, sigma x is acting, and similarly 2 shear force components are also generated. Okay, and those shear force components we can see here as parallel to the surface, parallel to this direction, area direction. One is tau xz, another one is tau another one will be a tau x y direction, xz, one is tau xym. Actually this one is tau xy and this one is tau xz. 2 shear force components in x directions, z and y direction also generated, and this force is acting in x direction. Normal stress will be in x direction. Remaining 2 parameters shear force components will be in z direction and y direction. This is one face of the xy coordinate, xz coordinate. Another face of the xz coordinate, there we can see x dash x. This is acting perpendicular to the sigma x. Sigma x dash is acting perpendicular to the sigma x, whereas sigma x dash will be indicated like this. If you see here, sigma x dash has been indicated with the change of the stress. Initially at this particular phase, nearer phase, sigma x value will be, we can see here sigma x value. Here at this phase it is sigma x, and when it is moves towards the x axis, the sigma x value has been increased with respect to direction. We can see here dou sigma x by dou x. It may be increase or decrease, but in that direction change of the stress will be there. Dou sigma x by dou x into del x. Here we can see the increase of the stress in x direction. Similarly, we have normal components of y, sigma y in this direction, and 2 shear components of remaining 2 components, z and x direction also we can see. Similarly, sigma y dash has been given here, and sigma z dash, sigma y dash has been given here, and tau yz dash and tau yx dash has been given here. Tau xy dash, yx dash, and tau yz dash. These 2 values we can see here. There also shear stress will be here. This particular location, it is tau yx and tau yz, but when it is moves towards this direction, at the depth of del y, there will be change of the stress. We can see change, increase of the stress will be dou tau yx by dou y into dy, and similarly for zy direction. And similarly we used to see for sigma z in the negative z direction here at this particular location, and sigma z dash in upward direction, positive direction. Sigma z dash value we can see here, and sigma other 2 components of shear stresses we can see here. Okay, here we can indicate it with this one. These all are the force stress components. Okay, stresses which are acting over that particular cross section areas or along the cross sectional areas. Okay. we used to utilize these equations to solve the equilibrium equation. Okay, here we used to take three equilibrium equations we have for resolving the forces. Here we are taking and also we have moment equilibrium equations 3. Okay, what we are going to do here, we are taking forces in force equilibrium equation in x direction. Okay, we are considering all the forces which are acting in x direction. Okay, here we can't take stresses directly. When we multiply these stresses with respect to area, those will be given as the force, whereas the stress is nothing but force by area. From that force by area we can get force is equal to stress into area. Same thing we used to apply here. This one will be the stress into area of the body. Okay, if you take positive direction sigma x dash is indicating sigma x dash, which is having the value of sigma x plus dou sigma x by dou x into dx. Okay, that one indicated with this one is the total increase of the stress, positive direction, and this surface area will be dz and dy in dz. That sigma x is acting normal to the plane of dy into dz. Okay, this one we wrote here. Okay, similarly another sigma x component, stress in x direction component, we can see here this is acting other side of this surface, this particular cross sectional area, and that cross sectional area is also having the area dy into dz, sigma x into dz into dz into dy. Okay, this one another one, negative direction. Similarly in x direction we have shear force components, like if you see here tau yx is there. Okay, at this particular surface tau yx is there, which is parallel to the x axis, and similarly tau yx dash, which is parallel to the x axis, whereas tau yx is positive direction, negative direction, where tau y dash x is positive direction, whereas tau y dash can be written as like this, tau yx plus dou tau yx by dou y into dy, and this one is acting over the area of dx into dz. This force is acting, stress is acting over the area of dx into dz. Here dz will be there, and another one dou yx, we can see here this dou y is also acting on this surface area of dou z into this dx value. Same thing, but it is acting in the negative direction. Okay, this is one, and another shear force component we can see here is is it visible? Screen is visible to you guys?
Yes, sir.
Yeah. If you take these forces, similarly we have force in z component. Okay, in the direction of z component, and which is parallel, which forces which are parallel to the x-axis. You can see here at the bottom side, you can see here tau xz, here bottom side you can see that is acting in negative x direction, tau zx minus tau zx, negative direction it is acting, and the surface of this parallel axis is dou y into dx, dy into dx surface it is acting. And similarly we have another one at the top of this face, this component, whereas x and y component, from the top view we can see x and y component. For that one also, in positive x-axis direction we have another shear component tau zx dash. This tau zx dash value is nothing but, here we can see tau zx value and dx into dy we used to take. This is regarding the force equilibrium, and addition to this one we used to have body force also. This whole body will have the volume v, and this volume will have some weight. That weight will be indicated in the direction of x. We used to indicate with the x into dx into dy into dz. This is the body force which is acting over that particular element. Okay, these all are the stresses which are acting perpendicular to the plane. Okay, these all are the forces which are acting. Yeah, here we can see different stress components. Okay, by using all these stresses, we used to derive into the force components. Here we have seen forces in x direction. What we have did, we have taken forces, stresses with respect to area. Okay, stress we have taken here, and we multiplied those with area of that particular stress is acting, area perpendicular to the normal stress. Similarly, area perpendicular to the normal stress. Here also area parallel to the shear stress, and here also area parallel to the shear stress component. And for this one also we are doing same thing, area. These all are the forces. Okay, these all are the force components which we used to use. Okay, after this what we have to do, which after simplification, okay, we have to do simplification. How we can simplify this one? By making higher order differential equation as 0. Okay, by making higher order differential equation as 0, or if you solve these equations, if you solve this equilibrium equation, you can get final equation like this: dou sigma x by dou x plus dou tau yx by dou y plus dou tau zx
Sir,
by
I can't hear.
dou z.
Yes, sir.
Yeah. After simplifying this equation, okay, when you simplify this equation, after simplification you can get the equation like this. Okay, here sigma x into dou y into dou z, it will get cancelled with the this one, sigma x into dou y into dou z. Okay, similarly here tau yx component, and here tau yx component, tau zx component, and minus tau zx component. After this you can get the equation, final equation like this. This is the differential equation for three-dimensional bodies: dou sigma x by dou x plus dou tau yx by dou y plus dou tau zx by dou z plus body force f of x is equal to 0. This is the final equation for three-dimensional body. Here we can see three coordinate systems in this one: x coordinate, y coordinate, and z coordinate also. And similarly we used to solve for other two directions also by using other two force equilibrium equation, summation of forces in y direction and z direction. We can get other extra force equilibrium equation or differential equation. Okay, equilibrium of differential equation we can see. These three equations are called as a three-dimensional differential equation. Okay, and after this we used to prove that tau yx and is equal to the tau xy. Okay, we have to show that shear force components are equal. Okay, same thing what we have did for two-dimensional body, same thing we used to apply here also. We used to take moment about z direction first case. Second case, if you take moment about other two directions also, you can get the equations like this. Same thing, mz will be taken moment at any point. If you make here O as your moment coordinate about this O point, about the z axis. Okay, about the z axis you can get the equations like this. Okay, there will be force into distance dy by 2. Okay, force into in direction of the force which is acting at the distance of dy by 2, normal distance. Okay, similarly here force shear force component into distance. Here also shear force component into distance dx by 2 for this one also. Okay, these are the forces which are acting in about the z axis. Okay, movements about the z axis. If you simplify this equation, you can get the final result as tau yx is equal to tau xy. This you can get from after solving this one. Okay, after solving this one we can get this one. Here in this equation we used to neglect higher orders. If you get here, if you see here dy and dy into dy, it will comes d square y. Okay, this is the higher order degree here, and this one get cancelled here. We used to neglect those two. Okay, it will be this term will become 0. Similarly here this term will become 0, and finally we used to left with tau yx and tau xy. Okay, and finally we used to get tau yx is equal to tau xy. And similarly, if you solve for by using other two equilibrium equations, moment equilibrium equations, you can get the equations like this: tau zx is equal to tau xz and tau yz is equal to tau zy. These all are the three-dimensional differential equations. If you see all the three-dimensional differential equations, equilibrium of three-dimensional equations, here you can see. Okay. With this, I am stopping for three-dimensional. I just take a break for 5 minutes. I will again join in 5 minutes.